Welcome to Introduction to Building Codes. Today's seminar is based upon the Bangladesh National Building Code 2020, referred to as BNBC 2020, Part 8 Building Services, Chapter 5 Water Supply, Part 2 Presentation, Water Distribution. The description of this presentation is designed to familiarize and assist code officials, inspectors, engineers, designers in not only locating the code sections, but describing and applying the applicable code requirements for air conditioning, heating, and ventilation systems. The overview of the course. Internationally, code officials recognize the need for a modern, up-to-date plumbing code that addresses the design and installation of plumbing systems through requirements emphasizing performance. This presentation will cover key topics of the following areas: purpose and scope, terminology, design of distribution systems, piping materials, protection of potable water supply, inspection, testing, and completion certificate. Our seminar goal today is for you to learn and apply key code requirements contained in Chapter 5 titled Water Supply, to enhance your performance while inspecting these systems. This training will also provide participants with specific code requirements, with examples related to design, installation, and inspection of water supply systems to further enhance your knowledge. Our objectives for this course today is that upon completion, participants will be better able to locate general topics within Chapter 5 titled Water Supply, as well as the specific topics that we will discuss and go over in detail. Additionally, locate applicable codes and standards for specific situations. Apply code requirements to real-world situations. We will explain the intent behind a given code requirement, normally based on its application, general and specific requirements. Use good judgment to identify certain systems and related components as either compliant or non-compliant. We utilize the code as a guide of requirements for public safety and good working characteristics of our water supply system. Some general information regarding water supply. Plumbing fixtures, devices, and appliances that require the use of water for proper operation are required to be connected to the water distribution system of the structure, which is then connected to an approved source of water, either a public or private source. Generally, approved water sources may be by means of public water utility. However, where potable public water supply is not available, individual sources of potable water may be used when approved. This is typical if there is no public water in the area of a proposed building. You would submit to the authority plans, specifications based upon the requirements set forth in this particular code for approval of that particular private water supply. Quite often, an individual source of potable water is a private or community well. It is common for both public and private or independent potable water sources to be regulated by agencies or departments outside of the typical building department. So as a participant in this seminar, we should be aware of who these agencies are that regulate different parts of the water system, from the water main to the water service pipe, and then into the building and the building's distribution system. Chapter 5, Section 5.1 gives us requirements regarding purpose and scope. The purpose of this chapter of the code is to provide minimum standards for the design, installation, and maintenance of water supply and distribution system within a building and its premises. So just reading that introduction sentence, you find that there are two different types of systems. The first one is called the water supply system. The second one is called the distribution system. The demarcation between the two can be looked at as the main shutoff valve at the building from the water supply connection that's tied to the main water at the public tap-in. So when we take a look at the water supply, we are looking for the proper design of this system, and it guarantees that the water remains drinkable and is not contaminated by any backflow condition or cross connection. We need the water to be safe and healthy for all of the occupants in the building. Drinkable water is viewed as a precious commodity by everybody, and it must meet minimum quality requirements. We will use this code as a guide to locate certain quality requirements as well. The authority has the responsibility for administering the code to ensure that water supplies to homes and the buildings in which people live and work are designed and installed to provide safe, clean, and healthy drinkable water. Section 5.1.2. The regulations of this chapter also provide guidelines for water requirements for different classes of buildings according to their occupancy classification. Water requirements for daily domestic use of a building shall be assessed on the basis of one or more or a combination of the following. This is where we estimate the water supply usage. The first one is water consumption for domestic purposes in residential buildings, cities, big district towns, areas like that. Socio-economic group, type of building, source, and other facilities must be taken into consideration with respect to the demand of water that must be supplied to these facilities. Water requirement for domestic purposes in residential buildings. This is in village areas and small communities, a scaled down version of what we found in the residential buildings up above for cities and big district towns. So based upon the use, location, and size of the residential buildings, there are two different methods here to figure the demand of this system. Domestic water requirements for various and other occupancies and facility groups. Now, Section 5.1.3 gives us the requirement for the provisions stated herein do not cover the requirements of water supply for industrial plants and processes, municipal uses, street washing, street hydrant, etc. So again, the water requirements are not covered for those specific operations and functions and buildings as well. Chapter 5, Section 5.2, Terminology. This section is very important that we understand the language in the code that we need to follow for water supply requirements. Many terms and sets of words have a very specific meaning based upon the code section requirements and tables listed in this particular code. So this section provides an alphabetical list of the terms used in and applicable in this chapter of the code. In case of any conflict or contradiction between the definition given in this section and that in Part 1, the meaning provided in this section shall govern for interpretation of the provisions of this chapter. Therefore, the specific words in this particular area of the code are specific and take precedence over Part 1. As you know, we will be talking about water supply systems, and the language indicated in this particular chapter will apply specifically. A code provision could be misinterpreted if the definition of a term as used in the context of the code is not understood. We must thoroughly understand the language. The following slides will provide key definitions that will assist the code user to properly understand certain terminology related to this chapter. Codes, by their very nature, are technical documents. As such, literally every word, term, and punctuation mark can add to or change the meaning of the intended result. This chapter contains several terms that are important to understand the provisions of this code. Definitions are found both in this chapter and throughout the code. Let's look at some key terminology. Our first term that we're going to study is the term accessible. And accessible has a very specific meaning. The definition of accessible is as follows. When applied to a fixture, appliance, or equipment shall mean having access thereto, but which may require the removal of an access panel or similar obstruction. Readily accessible shall mean direct access without the necessity of removing any panel, door, or similar obstruction. The picture below indicates a manifold water distribution system that is piped in, and at the very bottom of the manifold is a pressure reducing valve. This pressure reducing valve appears that it will be concealed between the studs in this particular construction. In order to be accessible for maintenance and adjustment and replacement of this pressure reducing valve, there needs to be a removable cover placed on this location to provide access to this pressure reducing valve. So upon the finish construction, the inspector would verify that this pressure reducing valve can be accessible by means of a cover that is easily removed
to access that particular valve.
Available head is defined as the head of water available at the point of consideration due to mains pressure or storage tank or any other source of pressure. Backflow is defined as the flow of water or other liquids, mixtures, or substances into the distribution pipes of a potable water supply from any source other than its intended use. This is something that we need to avoid. We need to avoid any other fluids, mixtures, other than potable water to gain access into the piping system. That's why we have backflow preventers. And by definition, a backflow preventer is a device or means to prevent backflow. As seen below, consider a boiler. A boiler has a connection to the potable water supply called makeup water. As can be seen in the graphic here, we have a backflow preventer with an intermediate atmospheric vent. Now, generally, there are three distinct classes of backflow equipment. There are assemblies, devices, and other means or methods. This class distinction clarifies that an assembly is field testable. A device is not testable in the field, and a mean or method is observable for its adequacy to protect the potable water supply from backflow. As can be seen here, this is a backflow preventer with check valves. As you can see, it's an intermediate atmospheric type vent designed to prevent backflow going from the boiler back into the potable water source. Based upon the pressure differentials between the check valves, lower pressures in the potable connection to the backflow will foul or translate the water through the intermediate atmospheric vent at the bottom of the backflow preventer, thus not allowing the water to migrate back into the potable water supply. This is one means of how we protect the potable water supply from backflow.
Full open valve is a shutoff valve that in the full open position has a straight through flow passageway with a diameter not less than one nominal pipe size smaller than nominal pipe size of the connecting pipe. Unlike shutoff valves and stops, full open valves cause very little resistance to flow and therefore cause minimal pressure loss downstream of the valve. Full open valves are also referred to as water service valve, and they include gate valves, ball valves, and butterfly valves. Full open valves are normally installed for main water service valves, normally installed at water meters, and at water heating appliances. The graphic indicates a full open ball valve, better known as a quarter turn valve or simply a ball valve. Tempered water. The water ranging in temperature from 29 degrees Celsius up to 43 degrees Celsius. Tempered water is specified in areas of the code regarding certain fixtures. A vacuum breaker is a type of backflow preventer installed on openings subject to normal atmospheric pressure. An example of atmospheric vacuum breakers screwed onto the threads of a hose faucet may also be acceptable as long as the connection is permanent. In other words, a locking type, or the threads between the hose faucet and the vacuum breaker are non-standard. This is a method of protecting the potable water supply. As seen here, these are hose connections that are typically screwed on to the faucet itself or the hose bib outside of the building. As can be seen here in the upper left-hand graphic, this is an at-rest condition. There appears to be two flexible seals. With the flexible seals at rest, there is a no-flow condition. The bottom graphic indicates water flowing. The inlet pressure is indicated on the top of that graphic. As water flows from the faucet through the device, you can see the flexible seals open and allow the water to pass through from the top to the bottom of this device that we call a vacuum breaker. In a at-rest condition, the flexible seals are closed, again referring to the upper left-hand portion. If there is any type of siphonage coming back through in the opposite direction of the water flowing, the seals will maintain a barrier and not permit the water to flow back into the potable water supply.
In section 5.5.1, buildings equipped with plumbing fixtures and used for human occupancy or habitation shall be provided with the supply of cold potable water in the amounts specified in sections 5.5.2 to 5.5.4 and at the pressure specified in sections 5.10.4.2 and 5.10.4.3. Those sections indicate the water distribution system. The importance of this particular section with respect to the water supply system is that only potable water shall be accessible to the plumbing fixtures supplying water for drinking, bathing, and culinary use, and for the processing of food. Additionally, 5.6 provides information for estimating total water supply demand using various methods. So the code user is directed to section 5.6 for specific information on estimating the total water demand. Section 5.8, Water Supply System. The main requirement here is each floor or unit within the water supply system shall be provided with a control valve in addition to the main control valve at the entrance of the system. One of the following public water supply systems shall be adopted for distributing water to the plumbing fixtures within the building. We are directed to see Appendix O. In the graphic below, we see the water service pipe coming from the city water main. We have a main water shutoff valve, And as the water piping connects the first floor and the second floor levels, we have separate control valves. So this is an example of a water supply system provided with a main control valve and separate floor control valves to control the water flow at each floor elevation.
Section 5.10, Design of Distribution System. Specifically referenced in Section 5.10.1, Rate of Flow of Water. A requirement in this part of the code indicates that one of the important items that need to be determined before the size of pipes and fittings for any part of the water piping system may be decided upon is the rate of flow in the service pipe, which in turn depends upon the number of hours for which the supply is available at sufficiently high pressure. If the number of hours for which the supply is available is less, there will be a large number of fittings in use simultaneously, and the rate of flow will be correspondingly large. So the data required for determining the size of the communication and service pipes are as follows. Item A indicates the maximum rate of discharge required at peak demand period. Now this is peak hourly demand of water, given by the equation total daily requirement of water indicated in the numerator and in the denominator divided by hours of water consumption. This is usually 15 to 17 hours of operation. And we multiply that times the peak factor, which is usually 2.2, depending on what the peak factor is based upon the use of the building and the building's fixtures. Item B, data required additionally is the length of the pipe. And in item C, the head loss by friction in pipes, fittings, and meters. For the head loss calculation in a piping system, we need to determine the total length of pipe and calculate the equivalent pipe length. In other words, head losses from bends, gate valves, reducers, and other equipment and fittings on the piping system from table 0.2 or appendix O of part 8. We will find specific information in appendix O for the design of the distribution system. We also need to consider the maximum permissible head loss of between 1.5 and 1.6 meter per 100 meter and assume the probable maximum velocity flow against tentative diameter of pipes as follows. For tentative diameter of pipe between 13 millimeters and 15 millimeters, we have a velocity to maintain between 0.3 and 0.6 meters per second. For a tentative diameter of pipe ranging from 75 millimeters to 100 millimeters, the velocity is given at 0.75 to 0.9 meters per second. And finally, for tentative diameter of pipe between 150 millimeters and 200 millimeters, we have a velocity range between 1.15 and 1.3 meters per second. Last is the determination of total head loss, given H sub F from the Hazen-Williams nomograph that's located in Appendix O, or friction loss formula, which is indicated as accordingly. H sub F equals 4 times the friction loss factor times the length of pipe times the velocity squared, divided by 2 times gravity times the diameter of pipe. This is given to us as a means to provide data required for determining the size of the communication and service pipes. Section 5.10.2, titled Discharge Computation, gives us another section based on fixture units. This is section 5.10.2.1. The design of the consumer's pipes, or the supply pipe to the fixtures, is based on A, the number and kind of fixtures installed, B, the fixture unit flow rate, and C, the probable simultaneous use of these fixtures. The rates at which water is desirably drawn into different types of fixtures are known. These rates become whole numbers of small size when they are expressed in a fixture unit. The fixture units for different sanitary appliances or groups of appliances are given in Table 8.5.4. Table 8.5.4 provides the type of fixture, the fixture demand in fixture unit, and minimum pipe size for the fixture branch. As an example, within the table, if we were looking for information regarding a shower in group per head, item number 4, the fixture unit as a load factor for this type of fixture is 3. The minimum size of fixture branch in millimeter for the shower in group per head is a minimum pipe size of 15 millimeters. If we have a wash basin for public use, item number 6, we find that the fixture unit value is 2. That is our load factor or demand for that public use wash basin. And again, the minimum size of the pipe for this particular type of fixture can be no less than 15 millimeters. General features of distribution system design are given to us specifically. Section 5.10.4.1 indicates the fixture supply system shall be designed to supply minimum but requisite quantity of water to all fixtures. Devices and appurtenances in every section of the building with adequate pressure. The design requirements of water supply system are presented in Table 8.5.6. As indicated below, Table 8.5.6 is titled Water Supply System Design Requirements. In the first column, the type of fixture is indicated. We have bathroom groups, bathtub, clothes washer, combination fixture, dishwashing machine, drinking fountain, kitchen sink, laundry tray, all the way down to 3 different types of water closets. The next column is our supply control. As we look at a particular fixture, like a kitchen sink, the type of supply control for a kitchen sink would be a faucet. If we have a water closet, further down the list, there are 3 distinct type of supply controls. For the first water closet, we have a flush tank supply control. The next one down is a flushometer tank. And then the last type of supply control for a water closet may be a flushometer valve. Now, if we stay here at the water closets for a flushometer valve supply control, the minimum size of the supply pipe is 25 millimeters. If we move up to the flushometer tank type water closet, the minimum pipe size goes down to 9 millimeters. As well as the flush tank type water closet, it remains at 19 millimeters. The next column is required fresh flow pressure in kilopascals. As seen here in the water closets, the flushometer valve requires much more flow pressure than the flushometer tank. 100 kPa for the flushometer valve, 55 kPa for the flushometer tank and flush tank. When we stay in this column for the required flow pressure, we will look at another example of another type of fixture like a kitchen sink. A kitchen sink must have a required flow pressure, that is a minimum flow pressure, at 55 kPa. And for the kitchen sink, we see in this case the minimum size of supply pipe cannot be any smaller than 13 millimeters. The last column gives the minimum or required flow rate in liters per minute. If we look at another example of a fixture, such as a drinking fountain, the required flow rate is very low, as can be seen here at 2.8 liters per minute. If we pick another fixture, such as a shower head with a mixing valve, the required flow rate at a minimum must be 11.4 liters per minute. So this is a valuable table to the designer to understand the minimum required flow pressure and flow rates along with the minimum pipe sizes for each specific fixture or fixture group. In section 5.10.4.2, we are given a requirement for a downfeed water distribution system. This is where we have a roof tank supply of water. Static pressure due to gravity increases with increasing floor height. Therefore, water distribution pipe in a building shall be maintained at a pressure so that none of their fittings are subject to a water head greater than 35 meters, or 345 kilopascals. In the graphic below, we see a downfeed water distribution system with a roof tank supply. On the very top of the building, water is introduced into this storage tank. From that point, we are relying on gravity to pressurize the water and flow downward to different zones, as can be seen, or different elevations of the building. We have our upper floor, which is called Zone 4. From the storage tank, we distribute water to the various fixtures on that floor. When we move to zone 3, the further that we run the pipe downward from the overhead storage tank, the more pressure is increasing within that distribution pipe. We need a valve called a pressure reducing valve to be placed in the pipe such that we do not have a water head greater than 35 meters, which equates to approximately 345 kilopascals. We do not want a high pressure in our piping system run to our fixtures. If you do have high pressures, it may damage fixtures and equipment that are not designed for elevated pressures. That's why we have this limitation. So the pressure reducing valve is seen in all of the downfeed distribution pipes from zone 3 to zone 2 to zone 1, providing a safe pressure to the piping that we call the water distribution piping that supplies the fixture and the fixture branches on each and every floor level below.
As directed in section 5.8, Appendix O gives us requirements for sizing of cold water supply and distribution piping. The water distribution within the building may be an upfeed or downfeed system. The design principles are the same for both the systems. The principal difference in calculation procedure is that in the upfeed system, the difference in elevation between the fixtures and the water supply main exerts pressure that supplies water into the fixtures. But the downfeed system, the difference in elevation between the fixtures and the roof storage tank provides pressure to overcome the pipe friction. The following are the recommended pipe sizing procedures. There are several here. The first one, 0.1, the sketch of the main lines, risers, and branches serving different fixtures will have to be drawn. That's first and foremost. It is a requirement. 0.2, determine the number and types of fixtures that will be required on the basis of Table 8.6.1 in Chapter 6. We will locate the fixtures. We will indicate how many fixtures, and this is a requirement based upon Table 8.6.1 in Chapter 6. 0.3, the demand weight of different fixture units may be computed in terms of water supply fixture units, or we say WSFU, in accordance with Table 8.0.1. We could use in 0.4 the peak demand load or maximum probable flow in liter per minute may be estimated with the data obtained in section 0.3 using figure 8.0.1, or on the basis of the number of occupants according to their occupancy classification specified in Table 8.5.1. In item 0.5, the equivalent length of the main lines, risers, and branches will be determined. The equivalent length of different fittings may be estimated on the basis of the data presented in the tables as follows. Table 8.0.2a, Table 8.0.2b, and Table 8.0.2c, or from manufacturer's specification. The total equivalent length is the sum of the equivalent lengths of all pipes and fittings. We need this to determine the pressure losses, not only in the pipe, but also the pipe fittings. 0.6. The pressure loss through water meter may be determined on the basis of their operating characteristics, as shown in figure 8.0.6, referencing the disc type water meter. The data for other types of water meters may be obtained from the manufacturer. Again, this water meter equipment, we call it, definitely has a pressure drop, and we need to know what the pressure drop is, because this is a loss in pressure that needs to be accounted for when we are designing our cold water supply piping system. Continuing on, 0.7, the minimum pressure required at different fixtures to produce adequate flow may be estimated on the basis of the type of fixtures or minimum size of supply pipe in accordance with Table 8.5.6. We have 0.8, which gives us an equation. The average pressure drop in kilopascals per meter of equivalent pipe length that may be computed as follows. The equation gives us where F sub P is the average available pressure loss in kilopascals per meter of equivalent length of pipe, equates to the quantity of pressure in the water main, or 0 for overhead gravity storage tanks. We look at the height in meters of the highest fixture above the water main, or difference in meters in elevation between the storage tank and the fixture under consideration. Again, we call this the head, or the total height of difference. F is the pressure loss in kilopascals through water meter or such other fittings, plus pressure required to produce adequate flow through the most remote fixture in upfeed system or the fixture under consideration in a downfeed type system. Once we have determined that quantity, we divide by L, which is our equivalent length of pipe in meters. And as you can see, the convention of signs is positive for downfeed systems and negative for upfeed systems. As we saw before with differences in gradients when we were talking about the water supply, any upward elevation from the point of supply to the point of delivery results in a pressure loss. Case in point, we see a negative sign for upfeed type systems. The following are the recommended pipe sizing procedures. In 0.7, the table was indicated as table 8.5.6. This table gives us water supply system design requirements. In this table, the fixtures are indicated in the first column. We have fixtures that are called bathroom group, bathtub, clothes washers, kitchen sink, laundry tray, service sink, and different types of water closets as indicated in the first column. It identifies the fixture that needs to be designed to be supplied by the water supply system. The second column gives us supply control, whether it is a flush tank, a flushometer valve, a faucet, or a mixing valve, the supply control. The third column gives us the minimum size of the supply pipe in millimeters. As an example, a kitchen sink. A kitchen sink is indicated as the fixture. The supply control is a faucet. The minimum pipe supply must be not less than 13 millimeters. The fourth column gives us the required flow pressure in kPa. For the kitchen sink, having a minimum pipe diameter of 13 millimeters, we are required to have a required flow pressure of 55 kilopascals. The very last column, required flow rate in liters per minute. For the kitchen sink, our example, very last column, the required minimum flow rate is 9.5 liters per minute. So we can systematically pick the fixture or group of fixtures and obtain minimum pipe sizes, required flow pressures, and required flow rates. As an example, we continue on item 0.9. The pipe size may also be estimated from figures. Figure 8.0.5 to 8.0.10 for different types of piping materials on the basis of expected rate of flow determined in section 0.4 and the average pressure available for friction loss, F sub P, in section 0.8. Now, this particular figure that you're looking here is a logarithmic chart, and it gives us on the x-axis, or the lower level, the flow in liter per minute. On the y-axis, or the vertical axis, it gives us friction loss in kPa. This particular table figure is friction loss through taps and T's. So as an example, find the friction loss in kPa for a 19 millimeter T fitting with a flow of 50 liters per minute. We can simply go to the horizontal axis on the logarithmic scale. As can be seen, it starts at 10 liters per minute, so we move over to 50 liters per minute. 50 liters per minute, we rise up and intersect with the diagonal curve indicated at 19 millimeters. Once we intersect that curve, we move to the vertical axis and read the friction loss in kilopascals, which in this case, for a 19 millimeter T with a flow rate of 50 liters per minute, we have the friction loss of 8 kilopascals. And the designer would continue to do this for different types of fittings throughout the water supply system and determine the total friction loss by calculating that along with the friction loss in the pipe as well.
Another example is locating figure 8.0.10, friction loss in copper pipe. We are referenced to this figure above in 0.9. Therefore, friction loss in pipe is important to the designer. We need to know what type of friction loss that we have in kPa per meter. A simple way to figure this out with respect to copper pipe is the figure as indicated. On the x-axis, we are given friction loss in kPa per meter length. On the y-axis, we are given flow in liters per minute. The curves are indicated according to the pipe size that ranges from 19 millimeters to 150 millimeters. The type of pipe as seen here in the lower portion of the curves is type M, type L, and type K copper pipe. Type K is your thickest wall copper. Type L is your medium wall thickness, and type M is your thinnest wall copper pipe permitted to be used. As an example, we want to find the friction loss in kPa per meter for a 19 millimeter type K copper pipe with a flow rate of 30 liters per minute. Applying the figure, we move to the left-hand side of the figure and locate 30 liters per minute. We then move horizontally across until we intersect the type K curve for that material, which is type K copper pipe. Once we intersect the curve, we then move downward to the x-axis and read the friction loss as seen here at 3.3 kPa per meter. This gives us a loss, friction loss, per meter of pipe that can then be used in the hydraulic calculations for the water distribution pipe. When we have elevation differences in our buildings, running piping from a lower elevation to a higher elevation, we need to be concerned with how that affects the pressure in the piping system. As an example, at the lower portion of the piping system as indicated in the drawing, we have a pressure at the bottom of this particular riser of 354 kilopascals. We have a 5 meter elevation difference in the upward direction. We need to supply water to a second floor. Looking at the equation in the upper right-hand corner, pressure difference, P equals H times 9.81 kPa, where P is the water pressure in kPa, H is the head or the elevation difference in meters, and 9.81 kPa equals the pressure resulting from 1 meter head of water under the force of gravity. In our example, we will use a sign convention in the upward direction as a pressure loss. So our pressure loss, according to this graphic, we will use a negative number to denote pressure loss at the top of the pipe due to elevation difference regarding available static pressure from the bottom of the pipe. As an example, we take the pressure at the bottom of the water distribution pipe, P sub B, equaling 354 kPa. Our elevation difference is 5 meters. We can rewrite the equation as a pressure loss, PL, equals negative H times 9.81. Working that through, the product then becomes pressure loss of negative 49 kPa is our pressure loss. We then figure what the available static pressure would be at the top of the pipe. So our pressure at the top of the pipe would equal the pressure starting at the bottom of the pipe at 354 kPa minus 49 kPa. The resulting pressure at the top of the pipe would therefore be 305 kPa. A note that the designers must also consider friction losses in the piping, flow characteristics, fittings, and connected equipment as well as part of the rest of the hydraulic calculations for the distribution system. Section 5.12, Hot Water Supply Installation. This section gives us the requirements for hot water distribution, piping requirements, as well as hot water storage requirements. A water heater is any appliance that heats potable water and supplies it to the hot water distribution system of the building. In other words, we need a source to produce hot water. Wherever hot water is stored in a closed vessel, perhaps a tank, there is a potential for explosion. There are documented cases where improperly installed or poorly maintained storage water heaters have exploded with such force that they have been propelled through floor and roof assemblies in over 30 meters in the air. Very dangerous situation if not installed properly. This section is intended to regulate the materials, design, and installation of water heaters and related safety devices in order to protect property and life. Section 5.12.1, Hot Water Requirements. For a residential building, hot water may be supplied to all plumbing fixtures and equipment used for bathing, washing, cleansing, laundry, and culinary purposes. For a non-residential building, hot water may be supplied for bathing and washing purposes. Water requirement for hot water supply shall be in accordance with Section 5.5. This section provides requirements for hot water to be supplied to residential and non-residential plumbing fixtures, with a reference to Section 5.5. A note to the code user, in Section 5.19.2 requires all hospitals to be equipped to supply hot water as required by different fixtures and equipment. As seen here, we have a residential bathtub fixture that must be piped with a hot water supply. Non-residential washing machine is shown here, maybe a commercial washing machine, again needing a source or supply of hot water to be piped to this particular appliance. And last is the hospital clinic sink, where we need hot water to be supplied to this particular fixture located within a hospital. And again, we can see the requirements, all and inclusive, coming from Section 5.12.1 and Additionally, for hospitals, we need to go for the requirement located in section 5.19.2. Storage temperature requirements are given in section 5.12.2. The design of hot water supply system may be based upon the following temperature requirement. We note that scalding is a minimum temperature occurring at 68 degrees Celsius. Hot bath, design of the hot water supply for this particular application, has a maximum temperature of 41 degrees Celsius. A warm bath application would be 37 degrees Celsius. Tepid bath, 30 degrees Celsius. And a sink would be designed for a maximum of 60 degrees Celsius. This section does provide requirements for maximum temperature limits regarding designing hot water systems. In section 5.12.3, the capacity of hot water vessel shall be based on the maximum short time demand of the present premises. This gives us the storage capacity accordingly. Section 5.12.4, hot water heater. The hot water heater shall conform to the following standards: BS 758, BS 779, BS 843, BS 855, BS 1250, BS 2883, and those specified in Part 5 of this code. This is very specific for the hot water heater. Standards must be followed. Manufacturing standards, testing standards, to verify that the hot water heater utilized as an appliance has been tested and is safe for the installation. Section 5.12.5, cold water supply connection to water heaters. The connection of cold water supply piping into a water heater shall be made near its bottom. The minimum size of cold water supply piping shall be based on the probable hot water demand of different fixtures, but not less than 25 millimeters. The supply pipe shall deliver cold water into hot water cylinder as follows. A, the water heater, either electric or gas, of less than 15 liters storage capacity may be directly connected to the water main through a non-return valve. If we see the graphic below, we have a water heater, less than 15 liters storage capacity, with a non-return valve piped in accordingly. So the cold water piping above the water heater contains the branch, and then the non-return valve is piped in accordingly before it enters the water heater. Item B, the storage heater of 20 to 70 liters capacity may be connected directly to the water main through a non-return valve, and with an additional device that will prevent the siphonage of hot water back to the main. So this section gives us specific information and requirements, not only for minimum pipe size of 25 millimeters, but also connection requirements and capacity requirements for water heaters and storage capacity criteria. Continuing, item C indicates the enclosed water heater with storage capacity greater than 70 liters shall be fed from the storage tank. The water heater shall not be connected directly to the water main. And last, item D, the water supply connection to an open vessel type water heater may be made with an air gap of at least 15 millimeters above the top edge of the water heater. Ball valve connections shall not be used to control the flow of water into this heater. We are showing below a closed type water heater. This is not an open vessel. This is a pressurized storage type water heater. And we have a minimum 25 millimeter cold supply pipe feeding the water heater. Within water heaters, manufacturers install dip tubes, and this allows the cold water to supply this particular type of water heater through all the way down to the bottom of the water heater. Section 5.12.6 gives us a requirement for the hot water distribution piping. The connection of hot water distribution pipe to the hot water cylinder shall be at the top of the cylinder. The installation of piping shall be as to avoid airlock. In the case of hot water horizontal piping, the gradient shall be less than 1 in 250. As seen in the graphic, we have our hot water coming off of the top of the closed type water heater, and from that point it will be distributed throughout the building accordingly. But keep in mind we do have the horizontal piping gradient that is referenced in section 5.12.6. When we supply hot water to fixture outlets, we need to understand that there is a limitation to the length of piping that supplies the hot water to the fixture. A significant amount of water can be wasted by a fixture user while waiting for hot water to arrive at the fixture. In addition to being an inconvenience, the cost for the water, for the energy to heat the water, and for the disposal of the water are literally going down the drain. In other words, we don't want to waste energy, we don't want to waste hot water, and we don't want to waste water going down the drain. There will be less waste and inconvenience at the fixture where the source of the hot water is located near to the fixture. The drawing below shows a water heater with a recirculating pump. In other words, we've got a recirculating hot water loop is what we call it. The hot water coming from the top of the water heater goes horizontally to the draw-off pipe. It is then tapped in before comes down to the recirculating line, back through the circulating pump, and continues the pumping throughout that local hot water loop. We are actually extending the hot water pipe from the point of the recirculating line again to the draw-off pipe. This length is limited according to table 8.5.8. In section 5.12.6.2, we are given that the design consideration of hot water piping shall be such that the hot water will appear quickly at the outlet of different fixtures. To improve the situation, a secondary circulation system with flow and return pipe from and to the hot water cylinder may be adopted. The length of hot water distribution pipe measured along the pipe from the top of the draw-off tap to the hot water cylinder or the secondary circulation pipe shall not exceed the length prescribed in Table 8.5.8. The draw-off tap shall not be connected to the primary flow or return pipe. As seen in the drawing below, we have a draw-off pipe diameter of 19 millimeters. Our length is not permitted to be longer than 12 meters, as indicated in the table below. The table is titled Maximum Permissible Length of Hot Water Draw-Off Pipe. The first column gives us the largest internal diameter of the pipe. We have a 19 millimeter pipe. The length of the pipe is not permitted to exceed 12 meters, as seen here. We also have 20 millimeters to 25 millimeters and diameters that exceed 25 millimeters. And on the right-hand side, we'll give you the maximum length of pipe from that particular point in the hot water distribution system to the draw-off pipe and the tap accordingly. Section 5.12.9 contains safety device requirements regarding our hot water source. The temperature relief valve or pressure relief valve, or a combination of temperature and pressure relief valves, shall be installed for the equipment for heating or storage of hot water. The temperature relief valve shall be set at a maximum temperature of 99 degrees Celsius. The maximum pressure rating of the water heater shall not be more than 1000 kPa. The temperature relief valve shall be placed directly above the cylinder it serves, but in no case more than 75 millimeters away from the cylinder. The location of pressure relief valve shall be close to the equipment it serves, and there shall be no valve connection in between a relief valve and the hot water cylinder it serves. This section provides requirements for combination temperature and pressure relief valve or separate temperature relief and pressure valves to protect the water heater against possible explosion. Every storage tank type water heater must have both temperature and pressure relief protection to prevent tank failure. In many applications, the temperature and pressure, we say T and P, relief valve safety functions are accomplished by a single combination pressure and temperature relief valve. As seen in the picture to the left, there is a hot water storage appliance with a temperature and pressure combination valve. Combination temperature and pressure relief valve as shown. And it is not more than 75 feet away from the cylinder and appears to comply with the code so far. Every storage type water heater and storage tank must have both temperature and pressure relief protection. A relief valve is required to comply with the following, as indicated below. It must have a temperature setting of no more than 99 degrees Celsius. Must have a pressure setting not exceeding the tank rating but no greater than 1000 kPa. Temperature relief valve shall be placed directly above the cylinder it serves, but in no case more than 75 millimeters away from the cylinder. Many manufacturers have ports and installed temperature and pressure relief valves on the storage type water heaters as part of their testing and standard requirement. As seen here, we have a manufactured storage type electrical water heater that has been manufactured in accordance with standards and has a factory installed temperature and pressure relief valve installed on the storage type water heater. Section 5.12.10, Waste from Relief Valve. We need to make sure that the outlet of pressure, temperature, or other such valves are not directly connected to the drainage system. The relief valve discharge draining piping system, indicated to the right, indicates that there is a separate relief valve waste piping system. And in this case, it is not directly connected to the drainage system. If we follow along on the very top level of the building, we have a storage type water heater with a temperature and pressure relief valve, and the discharge pipe indirectly drains in by means of an air gap into a drain. The drain then goes through the floor and picks up the water heater TNP drain from the second floor. And we run that pipe all the way down to the first floor and pick up the TNP drain from the first floor water heater, and then go down into the lower level and indirectly discharge the waste into the floor drain. Again, it is not directly connected to the drainage system. The piping and the fittings of all these materials must be rated to handle the relief valve temperatures. So when you see this out in the field, we must verify that the piping is adequate to handle the elevated temperatures. If the water heater is operating properly, the pressure in the water distribution system is not greater than it is required by the code, and the relief valve is in proper operating condition. There should not be any water discharging from the relief valve.
Section 5.13 is the materials section. We have several different types of materials to choose from with respect to water supply systems. The materials and fittings for water supply and distribution pipe and for storage tank shall comply with the standards listed in Part 5 of this code and those specified in this section. By referring to standards, we are guaranteed that the material will be durable and sustainable if specified correctly based upon the testing standards and the end use of the system by designing it according to these principles and standards that are given to us in this code. The materials chosen shall be resistant to corrosion, both inside and outside, or shall be suitably protected against corrosion and free from all toxic and harmful substances. Polyethylene and unplasticized PVC pipe shall not be installed near hot water pipes or near any other heat source, due to the fact that these materials will combust, they will melt, they will deform near high heat sources. All joining of pipes and fitting shall be done in accordance with acceptable standard practices. This is how we connect the pipes, either by welding, brazing, threaded fittings, soldering, different types of joining methods with the associated fittings.
Section 5.13.1 gives us the requirements for water supply, service, and distribution pipes. Water supply, service, and distribution pipes shall conform to the standards that are listed in tables 8.5.9 and 8.5.10. The water supply pipes and tubing used outside of the building or underground shall have a minimum working pressure of 1.1 megapascals at 23 degrees Celsius. In case of water supply exceeding 1.1 MPa pressure, the piping material shall have at least a rated working pressure equal to the highest available pressure. Additionally, the hot water distribution piping shall have a minimum pressure of 550 kPa at 80 degrees Celsius. Different types or classes of unplasticized PVC pipes, better known as UPVC, are used for both service and internal distribution pipes as described in Table 8.5.11. However, polyvinyl chloride plastic pipe shall not be used exposed and unprotected as riser or water distribution pipe. Polyethylene or unplasticized PVC pipe shall not be installed near heaters or hot water piping. Lead pipes may be used only for flushing and overflow purposes in a water supply system. This section provides requirements for minimum working pressure, maximum working pressure, temperature limit regarding distribution piping. Section 5.13.2 gives us requirements for pipe fittings. The pipe fittings shall be in accordance with the standards that are listed in Table 8.5.12 and specified in Part 5. We will take a look at these tables and the standards that are listed for these fittings. Our first table that we will analyze is for water distribution pipe. Table 8.5.10. The left-hand side of the table gives us the materials for water distribution pipe. Brass pipe, copper or copper alloy pipe, copper or copper alloy tubing, CPVC plastic pipe and tubing, galvanized steel pipe, and PVC plastic pipe. On the right-hand column is the standard for that particular type of material. This table provides acceptable piping materials and associated standards for water distribution piping. Applying the table 8.5.10 for water distribution pipe materials, we find a copper tubing that may be selected for our water distribution system. The associated standard is ASTM B88 for that particular copper tubing material. PVC plastic pipe, Schedule 40 PVC plastic pipe has the standard ASTM D1785 for that particular material. As you can see, there are different standards, and the designer must pick or select the correct standard based upon the piping that is being designed for the water distribution system. The next table is Table 8.5.11a. working pressure range of different types of unplasticized PVC pipes. Now, the difference between PVC and unplasticized PVC is that PVC contains plasticizers that make it more flexible. UPVC doesn't have the plasticizers integrated into the materials during the manufacturing of that particular type of piping material. Therefore, unplasticized PVC is considered a rigid type of PVC. Applying the table, material unplasticized PVC pipe, type and class, we have class B, C, D, and E, along with the different pressure ranges for these classifications of pipes. Table 8.5.11b gives us the average wall thickness, particularly for Class E unplasticized PVC pipes. As can be seen here, the average wall thickness of Class E unplasticized pipes are as follows: 3/8 of an inch or 9.5 millimeters in diameter gives us an average wall thickness of 1.9 millimeters. 13 millimeter diameter gives us a wall thickness of 2.1 millimeters. 19 millimeter diameter gives us a wall thickness of 2.5 millimeters. And finally, 25 millimeter diameter gives us a wall thickness of 2.7 millimeters. We also have a table regarding pipe fittings. This is table 8.5.12. Materials are indicated on the left-hand side of the table for associated pipe fittings, and the standards are listed in the right-hand column. As an example, a copper solder fitting meets or requires the standard to be met of the standard ASME B16.22 for copper soldered fitting. Schedule 40 PVC socket fitting. We have the standard associated with that particular fitting as ASTM D2466. Again, you need to associate the correct standard with the particular fitting and material of fitting for the distribution system. Section 5.15.2 provides us with backflow prevention requirements. Item A indicates the installation shall be such that water delivered is not liable to become contaminated, or that contamination of the public water supply does not occur. Item B, the various types of piping and mechanical devices acceptable for backflow protection are the following: barometric loop, air gap, atmosphere vacuum breaker, pressure vacuum breaker, double check valve, and reduced pressure backflow device. C, the installation shall not adversely affect drinking water by materials in contact with the water being unsuitable for the purpose as a result of backflow of water from water fittings or water using appliances into pipework connected to mains or to other fittings and appliances, by cross connection between pipes conveying water supplied by the water undertaker with pipes conveying water from some other source, and by stagnation particularly at high temperatures. This section provides specific backflow prevention assemblies and devices to protect the potable water supply. When we have the need to provide backflow prevention, Item I gives us some specifics on how to do this. A backflow prevention device shall be arranged or connected at or as near as practical to each point of delivery and use of water. Appliances with built-in backflow prevention shall be capable of passing the test. All backflow prevention devices shall be installed so they are accessible for examination, repair, or replacement. Such devices shall be capable of being tested periodically by the authority to ensure that the device is functioning efficiently and no backflow is occurring at any time. As an example, an automatic fire sprinkler system that is connected to a building's potable water supply system must have a backflow preventer at that connection to prevent the possibility of the backflow of sprinkler system water into the potable water supply. A wet fire sprinkler system, although initially filled with potable water, will eventually contain stagnant water because there is not normally any flow in the sprinkler system to periodically flush out old water. Therefore, we must have some type of backflow preventer. As seen in the drawing, we have the automatic fire sprinkler system being supplied through a double check valve assembly. The water flows in, as seen on the right-hand side, through the water service pipe. We have service valves, a water meter, and before it goes into the double check valve assembly, we have water supplied to the water distribution system accordingly. Thus, the double check valve prevents backflowing into the potable water system. Where antifreeze or other chemicals are added to a sprinkler system or a standpipe system, or where a non-potable secondary water supply is or could be connected to the sprinkler or standpipe system, the potable water supply must be protected with a reduced pressure principle fire protection backflow prevention assembly. This gives us better protection in case of contamination being backflowed into the potable water supply. Section 5.17, Hangers and Support. The piping system shall be installed with proper support hangers and support to minimize undue strains and stresses. All fixtures and fittings shall be provided with hangers and support to secure them properly. Now, securing and supporting not only supports the pipe weight itself, but also the fluid contents within the piping system. In this case, we are talking about water supply and water distribution piping systems. As an example, we have pipe bent support maintaining a bend radius on the left-hand side. As the picture is shown, we have plastic materials that have been run with supports and adequate bending support as well. To the right-hand side, we have a plastic insert for copper tubing installed through metal studs that not only supports the pipe, but also protects it from the sharp metal edge of the metal stud. Section 5.17.2 provides us with a hanger spacing requirement. Vertical and horizontal piping shall be supported in accordance with Table 8.5.14. Locating the table in the first column gives us the piping material: galvanized steel pipe, copper pipe or copper alloy tubing greater than 38 millimeters in diameter, copper pipe or copper alloy tubing less than 38 millimeters in diameter, PVC pipe and tubing, aluminum tubing, and brass pipe. The next column gives us the maximum horizontal spacing in meters. And the very last column gives us the maximum vertical spacing in meters. So it is dependent upon the material and in some cases the diameter of the piping material will provide requirements for horizontal and vertical spacing. The drawing below indicates piping supported from the structure of the building with hangers for the cold water distribution and hot water distribution. We can apply this particular table based upon piping material and horizontal spacing. As an example, if we have copper tubing 19 millimeter in diameter for the hot water and cold water distribution pipes, we can utilize the table above and go into the copper pipe or copper alloy tubing that is less than 38 millimeters in diameter, and we will find that our maximum horizontal spacing for 19 millimeter cold water and hot water distribution piping must have a horizontal spacing between hangers of not more than 2 meters accordingly to this table. Section 5.18, Protection of Potable Water Supply. In Section 5.18.1, potable water systems shall be protected against non-potable water sources or waste, whether they're solid, liquids, or gases. There shall be no cross-connection between potable water distribution system and non-potable water distribution or waste disposal system. This gives us a clear-cut requirement that there is and cannot be any cross-connections. Section 5.18.2, Submerged Outlet. From potable water supply system shall be avoided. Connection of potable water to boiler feed water system or heating or cooling system shall be made through proper air gap. Section 5.18.3 references cooling water applications, where we use water for cooling or for other purposes. It shall not be returned to the potable water supply system. Section 5.18.4 gives us backflow requirements. Potable water supply system shall be protected against backflow either by air gap or by backflow preventer. Reflux non-return valve shall not be used for this purpose. Details are explained in section 5.15.2. Now this section provides a reference back to section 5.15.2 regarding specific backflow prevention assemblies and devices permitted to protect the potable water supply. In section 5.18.5, The connection of potable water for healthcare plumbing fixtures shall be protected against backflow in accordance with Table 8.5.15. This gives us water supply protection for hospital fixtures. As an example, if we take a fixture like a hose connection, the protection required is a vacuum breaker. As seen in the graphic up above, we have a hose faucet with an integral vacuum breaker built into it as it has been manufactured. There are also hose connection type vacuum breakers that we addressed earlier in terminology that would apply the same effect for the hose connection. And as can be seen here, specifically aspirators in hospital fixtures require vacuum breakers, bedpan washers require vacuum breakers, boiling type sterilizers must have an air gap as protection, exhaust condenser, flush floor drain, hose connection, and pressure sterilizer all have requirements for vacuum breakers. Section 5.20, Cleaning and Disinfecting the System. The new and repaired potable water system, including the storage tank, shall be disinfected before their use. The existing water supply system shall be cleaned and disinfected depending upon the quality of water. The storage tank shall be cleaned and disinfected at least once a year. Section 5.20.2 gives us the procedures. The following procedure may be adopted to disinfect the plumbing system. Item A. The water supply system or storage system shall be flushed with potable water until clean water appears at the outlets. Item B. The system or part thereof which requires disinfection shall be filled up with chlorinated water containing 50 milligrams per liter of chlorine for 24 hours, or for 3 hours with a chlorinated water of chlorine concentration of 200 milligrams per liter. Item C. After the period of disinfection, the system shall be flushed with potable water until the chlorine is completely removed from the water in the system. The above procedure shall be repeated until the bacteriological examination shows presence of no water contamination within the system. Pipe and pipe fittings are potentially exposed to a variety of pollutants and contaminants from manufacturing, handling, and installation. That's why it's so important to disinfect the complete system once the installation is complete. Disinfection is the only way to kill bacteria and microorganisms living within the potable water system. This section gives us a clear and specific way to disinfect the piping system.
Section 5.21 gives us requirements regarding inspection, testing, and a completion certificate. So piping and joints are not permitted to be enclosed. They're not permitted to be concealed or covered until they have been inspected and approved by the authority. All piping and fixtures shall be inspected for satisfactory supports and protection from damage and corrosion. So the authority must inspect all piping, all joints, all supports prior to any concealment or covering with earth. This is important so we can verify the materials have been used that are proper. The materials have been used that have been approved and that are in this code. The fittings have been made up according to proper installation standards. The correct size of pipes according to the construction documents is what we look for out in the field. And the bedding as well as the depth of the pipe accordingly. It's the responsibility of the permit holder or the agent to call for the required inspections before the work is concealed and to provide access to such work. In other words, if you have to climb down into a trench, you need to be very careful such that the trench is laterally supported so that it will not cave in. If you have to go down, make sure that that's the case. Make sure the safety is of the importance here, and there is safe access to the location that you need to verify all of the piping accordingly. If your inspection reveals that the work does not comply with the code or what the authority has approved, the inspector notifies the permit holder or the agent of the deficiencies requiring correction. Upon replacing, making the deficiencies whole again, the inspector must approve the corrected portions of the work before they are concealed. In other words, the inspectors must come back and verify that corrections have been made before concealment of the piping.
Section 5.21.2 references testing. After installation of the entire water supply system or part thereof, it shall be tested and approved by the authority before its use. Item B specifically indicates testing of distribution pipes and fixtures. The distribution system to be tested shall be slowly and carefully charged with water to expel all air from the system and to avoid all shocks and water hammer. The piping and fittings shall be absolutely watertight when all draw-off taps are closed. The system shall be able to maintain the pressures and flow required under working conditions. Item C gives us testing of the hot water system. The entire hot water system shall be tested for the maximum rated temperature and pressure of the hot water storage system. The system shall be able to maintain the required test pressure. All safety devices shall be tested for their proper operation. This section gives us specifics regarding the distribution pipes, the fixtures, the tightness of the system, as well as the hot water system itself. Testing the hot water storage system, all safety devices, making sure that the piping system has been tested for the rated temperature and pressure as well.
The completion certificate is indicated according to the requirement based upon Section 5.21.3. The licensed plumber shall issue the completion certificate in a prescribed form. The reference here is Appendix N. The plumber needs to issue the completion certificate to the authority on completion of the water supply system or any part thereof for inspection and testing. After testing, The authority will allow the water connection from the water main and give the final approval to use this section or to use the system if it's a brand new water supply system. This section requires that the licensed plumber submit a completion certificate to the authority as a function of providing specific information, such as piping location, owner information, name of the applicant, as well as technical information regarding the piping system. And again, the reference to Appendix N is given in this section for the completion. Appendix N indicates format of completion certificate, water supply works. This is a completion form that is filled out by the licensed plumber and submitted to the authority when the work is done. And as indicated here, it states certified that I or we have completed the plumbing work of water connection, given a number, for the premises as detailed below. This may be inspected and connection given. Again, ward number, road number, house number. The plumber must state the location of the work that has been performed. The plumber must indicate the owner, the owner's address, the applicant's name, the address and location, where the main is, and the size of the service pipe, the size of the ferrule, any number of traps, any number of closets, the capacity of underground reservoir where required. Now this could be an underground water storage tank connection as well. So the capacity has to be known and has to be stated here. Under the capacity, number of other fittings and appliances, any road cutting and repairing fee is indicated here. So the signature of the licensed plumber is required, and the name and address of the licensed plumber is required. On the bottom portion of this completion certificate is the authority's report certificate, and it indicates the following: certified that the communication and distribution pipes and all water fittings have been laid, applied, and executed in accordance with Chapter 5, Part 8 of the Bangladesh National Building Code, and satisfactory arrangements have been made for draining off wastewater. The water supply connection will be made on a predetermined date filled out by the authority and dated accordingly and indicated by the water supply authority. So this gives us a format and the form of a completion certificate that the plumbing licensed plumber will fill out upon completion and submit it to the authority for connection of the water supply system.
This is the end of the presentation. Thank you for your participation.